This is the 14th video in a series devoted to complex analysis. In the last video, we proved something called the Cauchy integral formula, and we're going to keep looking at some applications of complex integration here by looking at something called Morera's theorem and some of its corollaries. And so this theorem and its corollaries kind of fits into the following like flowchart of results. If you have a function that's continuous somewhere plus some additional structure, that implies that it's analytic. And maybe the point here is perhaps that additional structure that's on top of the continuity is easier to show to be true for some class of functions than the function being analytic just from scratch, from the definition of a function being analytic. Okay, so anyway, let's maybe look at the statement of Morera's theorem, and the first thing that we'll do is prove this theorem. So let's let f be continuous on a domain D. Then, if the integral over the boundary of R of f of z dz equals 0 for every rectangle R contained in D, where the edges of R are parallel to coordinate axes, then f is analytic on D. So this definitely follows into this flowchart down here. We have continuity plus more, and the more that we have here is that this integral along the outside of a rectangle is equal to 0. Okay, so now let's get into the proof. So we're actually going to make a little bit of a simplifying assumption to start off with, but this isn't really much of a simplifying assumption, and I'll talk about why it is actually more general than it might seem after we make this assumption. So let's assume that D is a disk centered at Z naught. So why this isn't quite as big of an assumption as it might seem is because since D is a domain, we can always find a disk centered at every point of that domain that's totally contained in the domain. Recall that a domain means that it's an open set, and the condition of getting a disk inside of that open set is the definition of it being an open set. Okay, great. So now we'll say for all z in D, we'll define a new function, and I'll call that function capital F of z, and that'll be the integral from z naught up to z of f of w dw. Since we don't know if f is analytic or not, we know that this may not be path independent, so we've got to talk about which path we are taking. So let's maybe get a picture over here. So let's draw our disk, which is centered at z naught, and let's put another point z within this disk. So the path that we'll take will be along this horizontal line. So notice that that is parallel to the real axis, and then up this vertical line. So it'll be something like that. And of course, that's if z is to the up and right of z naught. You could have similar pictures if z is situated kind of in another place. Okay, so now we're going to take the derivative of capital F, and we'll do that using this limit definition of the derivative. So we've got this is the limit as delta z goes to 0 of f of z plus delta z minus f of z over delta z. By the definition of f of z, capital F of z, I should say, we can simplify this a little bit. So this is going to be the limit as delta z goes to 0 of 1 over delta z times a certain integral, which we get from combining these two things together. So this is just from maybe calculus 1 style integration rules. So we'll have the integral from z to z plus delta z of f of w dw. And now we're going to sneak a copy of 0 into here. So we will add 0, but we'll add 0 in the following form. So we will add it as f of z minus f of z. And so that's maybe the trick that makes this whole thing work. Okay, so let's write that down a little bit more carefully. So this is going to be the limit as delta z goes to 0 of, now we have a bunch of stuff. So 1 over delta z times the integral from z to z naught of f of z dw. So that's that. And then plus 1 over delta z times the integral from z to z plus delta z. Sorry, this should have been z plus delta z of f of w minus f of z dw. So that's the kind of thing that we have here. But now let's notice that f of z is a constant with respect to this integral. So we just get the integral from z to z plus delta z of a constant. But that just gives us delta z because it's the endpoints subtracted. Obviously, the constant function is analytic, so that means it's path independent. We don't have to think too hard about that integral. So the delta z will cancel this delta z, and that means we'll get just f of z out of this term. Great, and then left over will be plus the limit as delta z goes to 0 of this stuff. So we have 1 over delta z, and then the integral from z to z plus delta z. Then we have f of w minus f of z dw. Great. So let's see what we have. We have f prime of z, capital F prime, equals little f of z plus this limit. So let's maybe bring that information to the top and then move on towards the end of this proof. So this is a cleaned up version of what we ended up with on the last board. So I moved my little f of z over. Now we have capital F prime minus f of z equals this limit that we had before. And now we're going to do a little bit of an epsilon argument to prove that this is in fact 0, this difference, and thus f prime is equal to f. So let's maybe take an arbitrary epsilon bigger than 0 and pick a delta bigger than 0 so that if the modulus of w minus z is less than delta, then the modulus of f of w minus f of z is less than epsilon. So that's possible because of the continuity of f. But now let's notice that means that if the delta z, its modulus is less than delta, then inside of this integral right here, so I'll just like bring this down. Maybe I'll put a green box to mean that stuff within the integral is less than epsilon. And why is that? That's because our w comes from between z and z plus delta z. Well, really any path between z and z plus delta z. But any path between z and z plus delta z will give us two numbers that are within delta of each other, and thus the difference of their modulus is smaller than epsilon. Okay, so, but since we're taking this limit as delta z goes to 0, at some point, all of the delta z's will be less than this delta. So that's good to know. Okay, so now to finish it off, we'll look at the modulus of f prime of z minus f of z, which now we know is less than or equal to the limit as delta z goes to 0 of, now it'll be 1 over delta z. I guess I should put 1 over the modulus of delta z. And then we'll have the integral from z to z plus delta z of the modulus of f of w minus f of z. So I use the triangle inequality for integrals there. And then dw. But now we know that this guy right here can be replaced with epsilon, and the inequality goes in the right direction. And then we just have epsilon times the length of any curve from z to z plus delta z. But now the longest path on any rectangle from z to z plus delta z will be exactly 2 delta z. So that means this is less than epsilon times 2 delta z over delta z, but that will be 2 epsilon. So what have we done? We've shown that f prime of z minus f of z can be made as small as we want. But since epsilon was chosen arbitrarily, that means that this is arbitrarily small, which means f prime of z is equal to f of z. But now let's recall that f prime of z being equal to f of z means that f prime is itself continuous because little f of z was continuous. So not only does the derivative of capital F exist, but it's continuous. But that's exactly the definition of it being analytic. So that means that capital F is analytic. But then in a previous video, we proved that if capital F is analytic, then any derivative of capital F would also be analytic, including the first derivative. So that means little f, which is equal to f prime, is also analytic. So again, that's by something we proved in the previous video. But that's exactly where we needed to end this thing. Okay, so now that we've proven this main result for the day, let's look at a couple of corollaries. So our first corollary has a lot to write down, but the proof is pretty nice. So let's suppose that for all t on the interval a to b, g evaluated at t and z is a continuous function on a domain D. If for each, again, t on the interval a, b, g, t, z is analytic, then this function defined in terms of the integral is also analytic. So we have capital G, which is the integral from a to b of g of t, z, dt is analytic on D. Okay, so let's see how we can do this. Obviously, we're going to use Morera's theorem because it's a corollary to that. So let's maybe suppose that R is a subset of D is a rectangle. Furthermore, maybe it must be a rectangle with edges parallel to the coordinate axes, but I won't write that down. Then let's notice by Cauchy's theorem. So remember, Cauchy's theorem talks about the integral of an analytic function over a closed curve being equal to 0. We have to pick the right closed curve, so that'll be the boundary of R. So we've got the integral over the boundary of R of g of t of z dz equals 0. And this is true for all t on that interval. And so again, that's because we're assuming analyticity for all of the GTZ. But now let's take this equation and integrate it over the interval a to b. So if we integrate 0 over the interval from a to b, we'll just get 0. Now we'll have the integral from a to b of the integral over dr of gtz dz and then dt. Great. And now we're going to swap the order of integration, which is okay because this g is analytic. And then remember, we can do that kind of stuff as long as we have smooth partial derivatives, but it being analytic is more than enough in order to switch the bounds of integration. So let's do that. So that gives us the integral over the region del r of the integral from a to b of g of tz dt dz. But now let's notice that that inside integral is just our capital G. So that gives us the integral over dr of capital G of z dz. So we have that is equal to 0, but then by Morera's theorem, that means that this capital G is analytic. And so that finishes this off. Capital G is analytic. Great. So now let's move on to our next corollary. Okay, one more corollary of Morera's theorem. And this corollary seems kind of crazy by statement, but it has a really nice proof. And I think maybe the technique of proof here is something really to pay attention to because it'll be useful when we apply complex integration techniques to real valued integrals. Okay, so let's jump into the proof. So by Morera's theorem, we really just need to check that if we take the integral over boundaries of any rectangles for f of z dz, we always get 0. But let's notice that by the way that we're subtracting off r, there are maybe 3 important types of rectangles to look at. We'll only really look at one of them because one of them is totally trivial and the other case is kind of wrapped up in the case that we'll look at. So maybe let's draw a picture here. And the first type of rectangle doesn't interact with the real axis at all. So it would be something like this. But notice if we take an integral around that boundary, we definitely get 0. And we definitely get 0 because we have an assumption of the integral being, or of the function being analytic there. Okay, so for our next example, we could have a rectangle that just butts up to the real axis. So maybe it would be something like this. And so that would be definitely a case that we would have to check, that if we have a rectangle like that, we also get 0 for the integral around that rectangle. And then finally, we need to look at an example where the rectangle maybe consumes part of the real axis. So something like this. And this will be the case that we look at. And the technique for proving that it's okay in the case like this will kind of give you an idea for how to prove this one carefully, and we'll leave that as a warm-up. Okay, so let's say that that is R, and now let's split R into 2 pieces. And those 2 pieces will be defined in terms of a limit. So let's maybe make it look like this. So we've got point here that's kind of stopping like that, and then it goes up like this, goes down like that, and goes around like that. So maybe we'll call this curve right here C plus, because it's maybe in the top part of the plane. And then we'll pick up down here and continue the rest of our curve R. So this would be maybe C minus. So essentially what we've done is just erased little parts of R right there. And we'll also do that in a way so that we're just epsilon shy of the real axis in both cases. But now by a continuity argument, we can see that the integral over the boundary of R of f of z dz will be equal to the limit as epsilon goes to 0 of each of these. So I'll write that as the integral over c plus of f of z dz plus the integral over c minus of f of z dz. So this limiting procedure patches these 2 curves together into our original R. So now we're going to take this and add and subtract the same integral, thus like really adding 0. And the integral that we will add and subtract has the following form. So it'll be the integral from a to b of f of t dt, where that's occurring along the real axis. And then maybe I should point out that by A, I mean this point on the real axis, and by B, I mean that point right there on the real axis. So I think that's like pretty clear. And furthermore, we'll complete this curve C plus and C minus into 2 rectangles. So let's do that. So we can complete that one like this, and that'll give us, let's see, going that way, and then this one will give us something going that way. And then let's remind ourselves that we are adding and subtracting this guy right here. Okay, so now let's start putting this all together. So this is going to be the limit as epsilon goes to 0 of, now we have the integral of c plus of f of z dz. So that's that top bit. And then plus the integral from a to b of f of t dt, but I'm going to write this as f of t plus I times epsilon dt. And because we're taking the limit as epsilon goes to 0, this positive integral here converges to the positive version of this pink. But another important thing about this is that this integral right here represents this line that we've patched onto C plus. Okay, and then we'll also have the limit as epsilon goes to 0 of what's happening in the bottom half. So this is going to be the integral over c minus of f of z dz. And then let's see, this goes back from b to a. So I'll just write it as plus the integral from b to a instead of minus the integral from a to b. So b to a of f of t minus I times epsilon dt. And so that's because in the limiting procedure, that will give us the same thing as this minus sign right here, because the I epsilon will go to 0. And then that gives us this bottom curve that we're patching on here. So I'll underline that as well. But now let's notice that C plus along with this guy gives us a closed rectangle that does not include the real axis. And that C minus plus that guy gives us a closed rectangle that also does not include the real axis. Maybe we would call those like R plus and R minus. So this ends up giving us the limit as epsilon goes to 0 of the integral over the boundary of R plus of f, and then plus the integral over the boundary of R minus of f. Where, like I just said, all of this stuff together right here can be called R plus. But now, since we know f is analytic if we're away from the real axis, well, that's essentially brought these things away from the real axis above and below. That means we get each of these as 0. 0 plus 0 is 0. But then by Morera's theorem, since that integral was 0 and this other one that we didn't check is also 0, that means that our function f is analytic. Okay, so now I'll leave you with a couple of warm-up problems. So here are 3 warm-up problems based on what we did today. The first is to finish the case in the last corollary that we didn't prove. So recall that that was a rectangle that just touched the real axis. The next one is deciding whether or not the integral from 1 to z of 1 over w dw is independent of the path from 1 to z. And then the third one is a little bit of a generalization of this last corollary that we proved. And it says to suppose that we have a line which I'll call L, which is in the complex plane, and f is continuous on D and analytic on D minus L. Then you want to show that f is analytic on D. And that's a good place to stop.